In concept G, we're just going to review the molecular shapes that you observed in the PhET simulation, just review a couple of things. So remember, all these shapes are going to result from orbitals of the atoms mixing together or hybridizing those central ones in order to find these hybrid orbitals, which allow us to have basically symmetrical different angles and that type of thing in our shapes. So the shape and orientation of a hybrid orbital maximizes the overlap with the other atom that it's bonding to, and these hybrid orbitals are going to result in the different bond angles that we saw and their geometries. So we have these geometries and they're based on the VSEPR theory, the valence shell electron pair repulsion theory. So a couple things to take note, and you've seen this in the simulation. Shared and unshared pairs of electrons are going to repel each other. The unshared pairs repel more strongly than the shared pairs. A double or triple bond, remember, counts as a single electron domain. And the shape of a molecular ion is the result of the shared and unshared pairs of electrons being placed as far apart from each other as possible, and that's the key point there. So the electron geometry of a molecule is based solely on the electron domains. It doesn't matter if those domains represent the bonded electrons or the lone pair electrons. So I'm looking at just the electron domains. Oh, the electron geometries. So with 2 domains, I have a linear geometry. With 3 domains, and again, these are all just electron geometries, I have trigonal planar. With 4, I have tetrahedral. 5 is trigonal bipyramidal, and 6 is octahedral. And you can see here, you've been given also a review of the different bond angles that you saw in the simulation. Linear has a bond angle of 180. Trigonal planar is 120, tetrahedral is 109.5. Trigonal bipyramidal is one with 2 different bond angles. You have the 120 bond angle as well as the 90 bond angle, and then octahedral, they're all 90 from each other. Now we know though that when some of these bonded pairs become lone pairs, it's going to change our angles and also change how we refer to their geometry. So if some of the electron domains include lone pairs, we can analyze the structure in terms of what we call molecular geometry. We are going to find that, remember, that those unshared or lone pair electrons repel each other more strongly, which will affect the bond angles. So originally, if all 3 of my electron domains are due to bonds and I get this trigonal planar, I get a 120-degree bond angle between each of those outside atoms. And my molecular geometry is trigonal planar. However, if one of those is due to a lone pair, we're going to find that that's going to push the 2 atoms closer together, so further away from the lone pair, that we would get less than 120, somewhere around 118. We also refer to this differently in our molecular geometry to be bent. I'm also going to look at 4 electron domains. We know originally that our tetrahedral shape has a bond angle of 109.5. However, if I change out one of those with a lone pair, we're going to find that that lone pair is going to repel those 3 atoms away from the lone pair, closer to each other. So we get a smaller bond angle than 109.5, somewhere around 107. And we refer to this shape as being trigonal pyramidal. And then finally, if I change out another bond for a lone pair, so I have 2 lone pairs similar to water, then I'm going to get an even smaller bond angle than 109.5, somewhere around 105, because they're going to push those 2 together, and then at that point I just have those 3 atoms there, so I get a bent structure. Now you should also be aware of 5 and 6 domains. Originally, remember, if all 5 are bonded together, we have those 2 bond angles of 90 and 120, and we have trigonal bipyramidal. If we change out 1 lone pair, we would have a seesaw shape. 2 lone pairs would be a T shape, and 3 lone pairs would be linear. Our seesaw and T shape would be the ones that you would get a smaller than expected bond angle. And for 6 domains where they're all 90 degrees from each other in the octahedral shape, having 1 lone pair change out would be square pyramidal, and then 2 lone pairs would give you square planar. The only one that would be affected by the bond angles would be the square planar, because it would push those atoms closer to this other center outer one. Alright, so you do need to be aware of each of those names and also the corresponding bond angles. We're all set.